Alright, well, hello again. Welcome to another physics lecture. So we've talked about electricity, electric charge, electric force, electric potential, that also being called voltage. And then talk some stuff about electric current, how electric forces can give rise to flow of charge, electric charge, usually electrons, and how that can be very useful in electric circuits. So making devices that are do pretty much all the day-to-day things that we take advantage of. The lights, this camera, the projector, the phone, computer, so many things rely on building off of the basic, there's a couple more components we didn't really talk about in terms of electric circuits, but we don't have much time, so I gave you most of the very basic parts of electric circuits, and out of that you can build a surprisingly wide variety of interesting and useful tools. Okay, so now we're talking about the kind of the other side of the coin, which is magnetism. And so we'll go, the first part of this lecture will be about magnetism, and then transition that into what's known as electromagnetic induction. Alright, so just a brief history maybe-ish about magnetism. So apparently that term comes from Magnesia, which was a district in ancient Greece. And we used that because these unusual sort of stones that were found in that district, they called them lodestones, they noticed that those lodestones would attract pieces of iron. So just like in the picture here, you got a little paper clip that's being attracted by one of those lodestones. We would just call it a magnetic rock now, maybe. Yeah, and apparently somewhere in the 12th century, it was the Chinese who first started fashioning these lodestones, or figuring out that they could make these into compasses. They could put these oddly attractive materials onto rotating swivels, and those swivels would align with north and south. So, connecting this back to electric fields, in electric fields, well, the basis is you have some electric charges. For the most part, we talked about electrons and protons, electrons being negatively charged, protons being positively charged. And just from the fact that they had electrical charge, they would produce electric fields, and those fields would then interact with other charges to give rise to electric forces. So if you have an electron and a proton next to each other, there's a negative and a positive, right? They would each create their own fields, and those fields would tell each other that they should be pulled together, because we know that unlike charges attract each other, right? So bam, we get pulled together. It turns out that magnetic fields are produced when you have electric charges that are in motion. So if you take an electron and you sing it along, you're going to produce some kind of magnetic field. So all magnetic fields is actually motion of electric charge. So that's why I said this is the other side of the coin. Electricity and magnetism are actually two aspects of the same fundamental property of nature, which we call electromagnetism. So when it comes to magnets and magnetic fields, we have things that are slightly different than the basis of the electric field, right? The base of the electric field is electric charge, but now it turns out that when electric charge is in motion, we create magnetic fields. And in magnetic fields, there are similar things to, say, the positive and negative charge of the positive and negative electric charge. And those analogous sort of things are what we call magnetic poles. So when we talk about magnetic fields, we're talking about usually a north pole and a south pole associated with those magnetic fields. And it's similar to electric charges in that like poles, like a north pole and a north pole, will repel each other. A south pole and a south pole will repel each other. And opposite poles, the north and the south pole, will attract each other. So they're similar to electric field or electric charges in that way, where likes repel each other and opposites attract each other. Unlike electric charges, though, you never have like a single north pole just by itself, or a single south pole just by itself. They always come in package deal. You always have whatever object you have is creating a magnetic field. if there are specific poles associated with it, there's a north pole and a south pole. So you have some examples of magnets here, right? So you have a bar magnet. So what it sounds like, it's a magnet that's in the shape of a bar. There's a north pole side and a south pole. And if you were to take another magnet, bar magnet, just like that one, and bring it up to it, then you'd be pointed the north side towards this north side, like poles, they would repel each other, and you'd feel this force where you couldn't actually get them back close together. It would be difficult to push them close together because they're repelling each other away. Whereas if you put the south pole towards it, then it would attract each other, and those bar magnets would probably slide together. Other common example of magnets are what we call horseshoe magnets, which is basically a long bar magnet that's been bent around. So in a horseshoe magnet, the ends are where we consider the poles to be. So we want to say the left end is the north pole, the right end is the south pole. It's not really exactly clear from the picture which one's which, but it doesn't really matter. And in this picture, there's actually little bits of iron. So like we already said before, iron gets attracted to magnets. I'll tell you more about why that is in a minute. And finally, another one we already mentioned was a compass. But it turns out a compass is essentially a very small bar magnet, usually tapered on each end so it points. But basically it's a bar magnet. It has a north pole side and a south pole side, and they're linear kind of way along like that. It's just a bar magnet that's put in such a position where it can actually freely rotate around. So even though magnetic poles are like electric charges, mostly alike because of this like repel opposites attract part, they're not electric charges, so we don't want to confuse the two things. So what about then the force that arises from magnetic fields? So just some observations. Iron can become magnetized, and iron is one of a few other metals which are classified as ferromagnetic. Ferromagnetic is a fancy way of saying it can be magnetized. It can become a magnet. And in that sense, it will easily be attracted by a magnet. So magnets will attract ferromagnetic metals, and like I said before, magnets are either going to attract or repel each other depending on which of the poles are sort of facing each other. Also, similar to electric fields, the further you get away from the magnet, the weaker the magnetic field is, the weaker magnetic force will be on any other magnet out there. So we just have some examples of magnet with a bunch of nails that are being attracted to it, right? Those nails have a lot of iron in them, so they're ferromagnetic materials that can be attracted to the magnets. This is just a little fridge magnet attracting a key ring. Again, the key ring probably has iron in it, so it can be attracted by that magnet. And then just some kind of silly, cartoonish pictures of magnets, but they get the idea across, where if you're trying to push a north and a north together, it's very difficult. They're going to try to push each other apart. And if you have a north and a south pole together, they're going to try to pull each other together again, try to keep them apart. They're also showing the magnetic field lines in this that picture, but we don't need to worry too much about that right now. I think we'll say more about that later. More about that right now. So in terms of a field, I mentioned magnetic field multiple times. Just like when we talked about electric charge, there are electric fields that are produced by electric charge. When you have a magnet, or any moving charge, and again, remember, it creates a magnetic field. But when you have a magnet, you can look at its magnetic field, what its magnetic field looks like, in a number of different ways. One of the ways is just taking tiny little pieces of iron, again, like shavings of iron, and dropping them all over around the magnet. The iron, since it is ferromagnetic, it can become magnetized in that magnetic field, and therefore it kind of wants to line up. It wants to align itself with the magnetic field. So just like this compass here, so on the left side, it hasn't really settled, but imagine that that picture, north is at the top of the image, right? So before the magnet has a chance to settle, it's off to the side somewhere. But once you stop moving it around, it then aligns itself with the magnetic field pointing towards the North Pole here. This is just an example of a tiny little magnet that wants to align with the magnetic field that it's in. So in a similar way, you have these tiny little iron filings, and they become magnetized in the magnetic field, and then they want to align themselves with that magnetic field. So if you sprinkle all of these iron filings all over, what you'll get is kind of a fuzzy picture of the field around this bar magnet. And what it turns out is that the magnetic field kind of bends around the outside from the north to the south. It also comes out the ends and comes all the way back around. You notice also maybe that along the axis of the bar magnet, it kind of goes out, straight outwards. Okay, so here we're going to see a little demonstration of this kind of visualizing magnetic field. And instead of just dropping iron filings all over and around the magnet, it's a little bit more clever if you have this container and you put some oil or some viscous liquid in there and just put a bunch of iron shavings in that. So essentially you kind of made it so that these iron filings are in this liquid and they can move around fairly easily. And so what he's going to do is he's going to take this like box almost of floating iron and put it next to a magnet. Right? And what you'll see is you're going to see the iron that it starts to align itself with the magnetic field of the magnet. And you'll see it starts to make that same sort of shape where the magnet is like along here, there's a north end and a south end, and the iron aligns around like this, and around the bottom, and around the ends. Slow motion here. Right, he gets right close enough that the iron becomes magnetized by the magnetic field, and it all aligns itself up with the magnetic field of that magnet. Okay, so just a little bit more about, not much more, about ferromagnetic materials in general. It turns out that there's only three elements that are ferromagnetic, so easily can become magnets. And that is iron, cobalt, and nickel. Part of what makes them ferromagnetic is that they have a similar atomic structure, and they're actually very close to each other. They're only one proton apart from each other, iron, cobalt, and nickel. And something else I'll go into more in a minute also is that it's actually the spin, the electrons are electrically charged, and it turns out that they're not just orbiting around the nucleus of an atom, they're actually spinning, in a sense, around their own axis. Like the Earth spins around the sun, but it also spins around its own axis. And it turns out that spin is actually what produces most of this magnetic field. And so, we're going to look at how not all metals, you might think all metals would be attracted by magnets, or maybe it seems that way, but as I was just pointed out, it's only ferromagnetic materials that will generally be attracted by a magnet, basically because they become magnetized themselves, and then the two magnets can attract each other. So here we have a number of different pieces of currency. You normally think about metals as being, in terms of currency, you think about coins. And it turns out that in the Eurozone they have coins, and some of them have steel in them. And steel is basically iron and carbon. So you have a lot of iron and steel. So some of these coins will have metal in them, or some of the coins will have iron in them, some of them don't. There were apparently these buffalo nickels were actually made out of nickel, and nickel is one of those ferromagnetic materials, so that one would be attracted by a magnet. Interestingly enough, there's also iron in ink that is used to print the US currency. So there's actually a little bit of iron inside of that dollar bill. And what does that mean? Well, if it's iron, it's ferromagnetic. If it's ferromagnetic, it can be magnetized and then attracted by a magnet. So let's do that. So there you go, he's got a couple of magnets, and they're not sticking to them, there's no like glue or anything. Just you get close enough, you magnetize the iron in that ink, and you're able to actually lift up the bill a little bit. Pretty interesting. See, even when from far away, you can see that the bill, once the iron starts to get magnetized, then attracts by the other magnet and will pull up to it. How about coins? Right. So again, coins are usually made out of some kind of metal. Turns out that in the 40s, they made pennies when they actually had Let me do some iron in it. I forgot, I didn't miss what it said. So yeah, so this is just comparing even this same 1 cent currency, but in different periods throughout the US history, that those coins were stamped out of different metals. So back in 43, there was some kind of ferromagnetic material, but in these more recent ones, it turns out that it's mostly zinc and copper. So these ones actually aren't ferromagnetic. They won't be attracted by a magnet. Okay, so now it's time to look a little bit closer at what it means for a material to be ferromagnetic and where that kind of comes from. I alluded to this a little bit when talking about the spin of an electron. So going back to one of the first things I said about magnetism is that it arises from moving electric charge. So if you have an electric charge that's in motion in some way, then you're going to create a magnetic field. So at the very, very, very small level, the atomic level, you can think of an atom. In a very simple way, you can think about an atom as like a solar system, where the nucleus is where the protons and the neutrons of the atom sit, and then outside that nucleus there's electrons that are swirling around. So just, it works well enough, it's a good enough approximation to just think about it as like our solar system. Like the sun is the nucleus, where all the protons and neutrons are, and the Earth then is the electron. It's just orbiting around the sun. So right there you already have this charge in motion, right? You have that electron, that negatively charged atom that's in motion. So that creates somewhat of a magnetic field. It turns out, however, that as I said before, the electron itself is in a sense spinning around its own axis. So just like the Earth is also spinning around its own axis, the electron kind of spins around its own axis as it goes around the nucleus. And it turns out that that spin is actually mostly where the magnetic field will be generated from. So in the picture here, you have the atom, and then we show the electron as this little, that little fuchsia red ball around the side, and it's that spinning that sort of creates the magnetic field. And that in general makes this atom act like a tiny little bar magnet. So the North Pole and South Pole, and that makes a magnetic field just like any other bar magnet would. It goes sort of out of that North Pole, it comes around to the South Pole. Right? Same picture of a bar magnet field. So what makes a material ferromagnetic is that there are essentially like clusters of atoms that all tend to want to align up in the same way so that their electrons are all spinning in the same direction. For us, it would sort of be, or for the solar system, you would sort of be like, if we have our solar system, then the solar system right next to us would kind of want to align in the same way so that its planets are spinning around the same sort of axis that our planets are. So iron and cobalt and nickel are all materials that will do that readily. And what that means is that in regions within that material, you'll get these things called magnetic domains. So there are essentially these chunks inside, very, very, very small too, made up of lots and lots of atoms, but still incredibly small. And we have this picture here to show something like that, where you look at a tiny little piece of that iron, and within that there are these magnetic domains. So those arrows are indicating that all the atoms in that material are sort of aligned in such a way, or aligned together, so that you create a tiny little magnet essentially, it's like pointing north to south pole, that arrow, the way the arrow points. So these domains are made up of a bunch of iron atoms, and in each of those domains, those iron atoms are kind of all aligned together. But in general, all of those domains can then be in all the different directions, right? The direction that one domain here is aligned doesn't necessarily have to line up with the one right next to it, or the one further away from it. So when all of the domains are random, right? When like the picture here, all the arrows are sort of just pointing in random directions, the material is not going to have a magnetic field, because all these different magnetic fields from the magnetic domains are sort of canceling each other out. It's just all this random direction. There's no overall coherent direction to the domains, so you get essentially no magnetic field. So yeah, so you kind of think about it as that down on the left there's a picture of actual iron, and then if you zoom in really close, you see these chunks, these domains within the iron, and those domains are all aligned with themselves, or within that domain, the atoms are aligned with that domain. And you go all the way down to the atomic scale, and that's where we get this, the fundamental building blocks of the magnetic field overall. So, if you have all these magnetic domains, and again, assume to begin with, it's a piece of iron, it has a bunch of domains. Those domains aren't aligned together, they're just all random different directions. Right, we have this picture like on the top here, you have unmagnetized iron. It still has its magnetic domains within it, but again, because they're all randomly directed, there's no overall magnetic field for the piece of iron. But if you take a strong magnet and you start bringing it close to that piece of iron, as you bring it closer, the magnetic field from this magnet is extending over to that non-magnetized iron. And all those magnetic domains, they're acting like little magnets, and they want to align with this stronger magnetic field. So as you bring the magnet in, you start to get somewhat of an alignment, more of an alignment of these domains than you had before. So if you only brought it kind of close to that magnet, then maybe you might get this middle picture where more of the domains are pointing towards the same direction, but they're not all really aligned. So you have a bit of magnetization, but it's not very highly magnetized. Maybe slightly magnetized, as they say here. And finally, if you bring that magnet close to it, right close to it, and it's a very strong magnet, then all of those magnetic domains within that first piece of iron are going to want to align with this magnetic field. It's a very strong magnetic field, it's strong throughout the whole piece of this iron, so it's able to align all of these iron atoms, or all these magnetic domains, which are made up of iron atoms. So now you have this strongly magnetized piece of iron on the left now. If you take away this strong magnet, you still have your strongly magnetized piece of iron, right? So you just created a magnet, essentially. So it's odd to think, but essentially you use magnets, you can use magnets to create more magnets. So this is what happens if you have a strong magnet, and say you go and pick up a paperclip with that magnet. You've probably seen this, maybe done this. You pick that up. What you're doing is magnetizing that paperclip so that now it's its own magnet and it's attracted to the original magnet that you started with. But now, since you've magnetized that paperclip, it can now actually, if you hang that one closer to another paperclip, it can now start to magnetize that other paperclip, and that other paperclip will be attracted to that first one. So you can end up making this sort of chain of paperclips. Paperclips are nice because they're very light, and the magnetic force doesn't have to be that strong to pick them up. If you have a very strong magnet, you can do this with nails, and in this picture, right, you essentially have this chain of nails where the magnet has magnetized the top one, and it's probably also playing a part to magnetize the other ones, but essentially there's a chain where each nail sort of magnetizes the next nail, and so they all become magnets and they stick together. Just go back real quick to point out that when you do magnetize a material, a piece of iron, with another magnet, you always end up creating a magnet that is in the position to be attracted to that first, to this strong magnet that you used to magnetize. So when I bring this south end of this strong magnet in, it's aligning all of those magnetic domains up such that they could want to be attracted to that south. So in the end, I end up creating a magnetic north pole on the side that I'm bringing that south pole into. And this will always happen. If you brought the north pole in, then all these magnetic domains would align the other way, and you'd end up creating magnetic south that would be attracted to that magnetic north. Okay, so there's actually, I have a video here of essentially a very strong magnet picking up a bunch of nails. I'm trying to keep this lecture a little bit shorter, so if you want to watch that one on your own, it's kind of cool because it's a very strong magnet, and the nails are embedded in, it looks like they've just been in a fire pit and been burned from maybe some construction pieces. So they're going to get pulled out and almost pop out of that fire pit. This is kind of interesting. So feel free to watch that, but we're not going to do that here. I will say though that given that you can magnetize things, and that magnetism is essentially an alignment of all those magnetic domains within the material, within iron, cobalt, or nickel, you can also demagnetize things. There's a number of different ways. I have some of them here. I guess these are the ones that you demagnetize without actually using another magnetic field, which you can do. But essentially, there's some very straightforward ways to demagnetize things. One is just through blunt force. If you hit the material, right? Start knocking a bar magnet, then what you're doing is jiggling all these magnetic domains, and all that force is going to just start kind of disaligning these magnetic domains again. Right? So you hit it very hard or hit it enough, then eventually those magnetic domains are going to be unaligned enough again. They're all going to be random directions, and you no longer have an overall magnetic field. Another way to demagnetize something is using heat. So if you heat a bar magnet up, remember from our discussion of the atomic picture of matter, heat is basically a transfer of energy, and when you transfer energy into a material, the atoms tend to start moving more and more. So when you heat a magnet up, you're essentially adding more motion to all those atoms, and that more and more motion tends to want to disalign those magnetic domains again. They get loose enough and they start moving around enough that they will de-align with themselves. They start to go in random directions again. And in a similar way, time can also just disalign a magnet. Essentially, the random motion of the atoms can eventually start to demagnetize. Okay, so that's still magnetic fields and magnets being produced by the motion of electric charges. In the fundamental sense, it's from the motion, the spin of those electrons around the proton, around the nucleus, and around its own axis. But anytime you have electric charges in motion, you're going to create a magnetic field. And a very simple example of that is electric current. So last time we talked about electric current, and it's literally just the flow of electric charge. Just like a river is the flow of H2O molecules, electric current is a flow of electrons usually, but charged particles. So any electric current, anytime you have an electric current flowing, you're going to have a magnetic field around that current. And it can be rather complicated how that magnetic field looks, but in the simple case, you can just think about you take a wire, a long straight wire, connect it to some kind of voltage source that you start flowing current through that wire. So maybe you're flowing current up this part of the wire. And it turns out that you're going to create a magnetic field that wraps around that wire. So the current's flowing up this way, or flowing upward, and the magnetic field is going to wrap around the wire like this. So this is the picture here. And you can see that if you were to take a bunch of compasses and place them around that straight wire, when you don't have any current flowing, those compasses are all going to be pointing towards geographic north. However, if you turn on a power source or connect that wire to a strong power source, because you want a good bit of current to create a powerful enough magnetic field, that when you turn that current on, you'll see all these magnets just flip and go align and point in a circle around that current carrying wire there. In the case of the magnetic field from this wire, it turns out there isn't necessarily a strict north pole and a south pole, because from that wire, the magnetic field is essentially a loop. It's looping around that wire. So there's no real sense that there's exactly a north pole or a south pole there. So now that we're clear that electric current, any electric current, being a flow of electric charge and movement of electric charge, will create a magnetic field. That's in turn why we are able to make things that we call electromagnets. They're essentially using electric current to create magnets. And as it turns out, if you take a wire you're going to flow current through, if you take a wire and you sort of, you can imagine just wrapping it around something, you make essentially a coil out of that wire. So in the picture here, we're only seeing half of this coil, but the wire sort of loops up and around, and then loops up and around, and loops up and around, and loops up and around, and loops up and around, loops around. And so you make this sort of coil with your wire. When you flow current through that coil, you end up creating a magnetic field. This is very similar to the magnetic field from a bar magnet. Technically, that shape is called a solenoid. Not really any need that word, but that's a technical term. But essentially, when you create, you take your coil and you pass current through it, you create, this magnetic field that sort of shoots out of the North Pole, somewhat comes around into the South Pole and goes into the South Pole, kind of flows around in this bending motion on the outside. The arrows are only shown on one side, but it's on both sides. You can see from the iron that the magnetic field of these objects is on both sides, and it's symmetric. Same on the left as on the right. And it's very similar to the bar magnet. So this is one way we create a magnet that acts like a bar magnet out of a coil of wire. So there you go, you can create an electromagnet, a magnet produced by the flow of electricity or current. So it also turns out that you can make an electromagnet out of a coil, and that's typically how it's done. On top of that, if you insert a ferromagnetic material inside of that coil, like in this picture here, we have this piece of wire and it wraps around a nail, right? So the nail is a piece of iron, so it's making up the core of this coil. That turns out to be able to create an even stronger electromagnet. So you can create a magnet just with the coil alone, but if you put a ferromagnetic material inside of that coil, it's even stronger electromagnet. And just like any other magnetic field, the strength of that field from the electromagnet is going to fall off as you get further away. It's less and less intense, but the strength of it dies down as you get further away from the source of it. But in the picture here, you see all we have is a battery and that piece of wire that coils around the nail, and that battery then is the source of our electric potential difference, so that our voltage source. So by connecting this wire to that battery, you're going to cause current to flow around that, through that wire, around that loop, and we create our electromagnet, which can then attract things like paper clips. So here he's got a coil of wire that's holding in his hand. It's a bunch of wire wrapped around the tube there, and I think he touched the paper clips without it. Oh, but it's essentially two ends of the wire that's coiled around there are connected to this battery, and the red clip either is attached or not attached. So when it's not attached, it's a broken circuit and you have no current flowing, right? So there's no current flowing when that thing's not attached, but once it's attached, we have a closed circuit. We can, this voltage source the battery is providing, cause current to flow. So we have current flowing through this coil of wire, we make an electromagnet. And it's only a magnet. You only get that magnetic field when the current is flowing. When he takes the clip off, no longer a magnet. Or no more magnetic field. Alright, so a chance to ask yourself a question or two here. And the second question kind of gives away the first question, so maybe let's just look at that real quick. When an object is charged with static electricity, is that object also magnetized? Turns out, no, it's not. Think about why that is true, or not necessarily true. And secondly, it says iron is magnetized when the electrons are aligned, right? All those electrons in making up the magnetic domains, and they all align. So if iron has electrons, why isn't it electrically charged? Press pause and think about those questions for a minute. Maybe hopefully write down an answer to it, and we'll see how you do. Alright, so as to the first question, like I told you, no, this object is not necessarily magnetized just because it has a static charge. When we were talking about electrostatics or static electricity, the main example was you take a plastic rod and a piece of fur and you rub those two things together, you create two statically charged objects. So when you're doing this movement, there can be movement of electric charge there, where the electrons are leaving the fur and going onto the rod. But once the two things are charged, you just have more electrons on this rod and I have less electrons on this fur. So this is negatively charged, this is positively charged. But now there's no real more movement of electric charge anymore. That's one of the reasons why we call static electricity or electrostatics. Because once that charge has moved already, we have statically charged objects, but that charge is not in motion. So just because you have static electricity doesn't mean you have a magnetic field. And as to why, even though iron has all these electrons that are aligned, why it's not electrically charged, well, remember that atoms are made up of electrons and protons and neutrons, but those don't really matter in this part. So even though you have all these electrons that are spinning and they're all their spins get aligned, so you get this whole overall magnetic field, those electrons, that negative charge of each of those electrons is usually balanced out by a positive charge of the protons in the nucleus. So in general, most materials will have an equal amount of electrons and protons. And since, well, in this case, we'll just imagine that this is a typical case and you have the same amount of electrons as you have protons, therefore there's the same amount of plus charges as you have minus charges, and there's no overall net electrical charge. That being the case doesn't mean it's not magnetized, remember, because the magnetism comes from the spin of that electron. Alright, so what about the Earth? You probably know that the Earth has its own magnetic field. So the reason why we can use compasses to navigate, though you may have never used a compass, but you know what the idea of a compass is. It turns out that migratory animals, like birds, seems like they actually use the Earth's magnetic field as well, in coordination with tiny, biomolecular mechanisms that also sort of act like compasses. I don't know the details, but they also will use the Earth's magnetic field to coordinate and figure out which way is north and which way is south and they'll migrate. So why is that? Well, what it looks like, if you just kind of take the big picture, it essentially looks like the Earth has this very large bar magnet inside of it, where you have the south pole at the top and the north pole of the magnet down at the bottom. Because whenever you're on the Earth, if you take a compass, that compass, the north pole, the magnetic north pole of the compass points towards the geographic north pole. But remember that for magnetic poles, just like electric charge, it's unlike poles that attract each other. So if your compass's magnetic north pole is being attracted to the geographic north pole, that means that there's actually a magnetic south pole within the Earth. There's some sort of at the top of the Earth here. And in the same vein, that means that there's a magnetic north pole near Earth's geographic south. So it's a little bit confusing, but kind of rely on our compasses telling us which direction the magnetic field is. So since the magnetic north is pulled towards the geographic north, that means that there is a magnetic south up there. But it's not the case that there's actually just a big hunk of iron that's magnetic. The magnetic domains within a huge chunk of iron within the Earth are all aligned, so we get this permanent magnet inside the Earth. It seems that the Earth's magnetic field is created more like an electromagnet. It's due to the flow of electrical charge within the Earth. So within the Earth, there's the different layers. We think of like the crust, the mantle, the outer core, the inner core, and in the more inner area of the Earth, there's a lot of iron, and that iron is mostly or largely in a molten form, meaning it's liquid. And as the Earth spins, it spins that iron around. And overall, it seems that there's a net electric charge, and that net electric charge is flowing around with that iron. So what we get is essentially a very large electric current. This big electric current that's sort of swirling around the axis of the Earth. Right? So the same way the Earth sort of swirls around with that current, electric current flowing around. And that, remember, produces essentially a magnetic field that looks like a bar magnet. Right? It's like we have a coil of wire where that current is spinning around on the inside. We produce this field that looks much like a bar magnet. So the fact that we have this magnetic field is very nice. It protects us from a lot of things that will rain down on us, either from the sun or from other extraterrestrial bodies or things in other solar systems and other galaxies. They're spraying out electrically charged particles, and if we didn't have this magnetic field, then those particles would rain down and they could be hazardous to us. Since we do have this magnetic field, those electric charged particles, since they're in motion, actually get directed along the magnetic field lines of the Earth. So, for instance, if you have an electrically charged particle and it zooms in towards the Earth, if it's up in the northern hemisphere, it ends up getting directed around these magnetic field lines and swirls around, and all comes directed down around near the North Pole. If it comes in around in the southern hemisphere, it gets directed towards the South Pole. And this is why we have the northern and the southern lights, or the northern aurora borealis and Aurora Australis, I think is what it's called. And those lights are essentially those electrically charged particles that are then slammed into the atmosphere and energize some of the atoms in the atmosphere, and then those atoms, when they let go of that energy, it's photons that they give off. They give it off as light energy. Okay, so the final thing about magnetic forces I'm going to talk about before we move on, well, more in depth into something called induction, is to say that just as electric forces arise from electric charge, electric charge will create an electric field, that field will act on other electric charges. So in the same way, magnetic fields are created by moving electric charges. You have an electron zooming along, it creates a magnetic field due to that motion. That magnetic field will then act on other moving charges. So in order for something to experience a magnetic force, it must also in some way have an electric charge in motion. So one easy way to see that is if you take the setup like we have here, where you have this horseshoe magnet. Right? The horseshoe magnet, again, is just like a bar magnet that's been bent. So there's a north pole and a south pole, and there's a magnetic field that's pointing from the north pole to the south pole. And if you take that magnet, that horseshoe magnet, and kind of drape a wire between it, and then connect that wire to some kind of power source, to some voltage source, you can force current, send current through that wire. And remember, again, current is just moving electric charge. Right? So now we have a magnetic field. You have charge that's moving through that magnetic field. That charge is going to experience a magnetic force. As a caveat here, you only get a magnetic force when the motion of that charged particle is not totally parallel to the magnetic field. The picture here, if you turn that horseshoe magnet sideways, then you have a magnetic field pointing sort of into the picture here. If we flow the current also into the picture here, you get no magnetic force on that current, because the motion of the charge in that current is along the same direction as the magnetic field. It turns out the magnetic field, or magnetic force, only arises when you have motion that is at least somewhat perpendicular or at an angle to the direction of the magnetic field. Right, so in this picture on the left, we have a magnetic field that's pointing sort of maybe right to left or left to right, and then you have a current that's coming across that field. Right? So the current is exactly perpendicular in this case, so you're definitely going to get a magnetic force. And it turns out that if the current flows one way in this picture, you get the force that would push that wire up, versus if you flow current the opposite direction, you're going to get a force in the opposite direction, push that wire down. Right, so in this video, basically that same sort of ideal setup, where now we have our magnet it's essentially like a horseshoe magnet, but it's been bent even more, so it kind of looks like this C shape. But again, the poles of the magnet are the ends of that, the inside of that C shape, the ends of the horseshoe magnet there. And the setup here is not quite as easy to see, but essentially he's connected this piece of metal, probably copper, that's hanging inside of that horseshoe magnet. And it's hanging, but it's connected to these other wires, and these other wires come back and are connected to a voltage source. So when he has these two leads, these clips, he connects the clips to the voltage source. You're going to flow current through that wire, and what we're going to see is that now that we have magnetic charge or electric charge moving through that piece of metal, it's moving inside of a magnetic field. It's moving perpendicular to the magnetic field. It's going to get pushed to the side. And then what he's going to do, he's going to flip the leads so the current flows the other way, and the force is going to flip and push the other way. Alright, so there you go. Get a better camera angle here. So now instead of the wire sitting in the middle, it got pushed to the one side, and when he flips the lead, if the lead's on that, the current flows the other direction, force goes the other direction, and the piece of metal there is pushed to the other side. So we just have magnetic force in action. So the magnetic field produces the big magnet produces a magnetic field. That magnetic field will act on moving electric charge. That moving electric charge in this case is the current flowing through that wire. So now we got to the subject of induction, or electromagnetic induction. And the term induction comes from, well, the word induced. So when you induce something to happen, or you're essentially causing something to happen, you're inducing an outcome. So I think keep that in mind when you think about induction. And yeah, so the basic idea is you can induce a potential difference or a voltage in an electrical circuit in a loop of wire just by moving a magnet around that loop of wire. The more sort of fundamental picture is that magnet has a magnetic field. So like in this picture here, you have our bar magnet, have this loop of wire. So you have a magnetic field for this bar magnet, and the magnetic field extends through that loop. But as I move that magnet, I'm changing the amount of magnetic field going through that loop. So as it's far away, there's some magnetic field in that loop, but there's not much because it's far away here, it's kind of weak. Now if I move that magnet closer, now there's a lot more magnetic field in there, it's much stronger. The magnetic field is much stronger in there, so I've changed the magnetic field through that loop. I can induce a voltage in that loop, which essentially is driving or will drive electrical current. In this picture, if you have a loop of wire and it's connected to this little meter, the meter is just going to show, it's meant to just show if there's current flowing in this loop. So if I take that magnet and I drop it down into the loop, it doesn't need to be around the loop like that, it could have just gone through the middle of the loop as well. But if I move it around this loop, then I'm going to see that this current meter is going to start moving because there's current flowing. So no physical connection between the magnet and the wire, but just by moving that magnet around the loop of wire, I can cause current to flow in that loop. And, well, essentially the faster you move that magnet, the more larger induced voltage you're going to get, the more current you're going to induce to flow. So more current flows in that loop if you move the magnet faster. And what's important in induction is really the relative motion of the, well in this case the magnet, but the source of the magnetic field and the loop of wire that you're causing current to flow in, you're inducing current to flow in. So in this picture it's showing on the one side we're showing the magnet moving up and down, and on the left side we're showing that if you have the magnet stationary and you move the loop of current around that magnet, you're also going to induce a voltage which will drive current. So as just maybe a more realistic picture of this happening, if we look down at these images at the bottom here, on the far left we have a bar magnet. Well, they all have the same things in them, but the materials or the things in them are the bar magnet. You have a coil or loops of wire, and in this picture they're showing that they're coiled around a piece of iron probably. It's not really necessary, but just the fact that it's a coil, we now have these loops of wire, and then eventually that coil is connected to what's called an ammeter, but it's basically it just measures current. It shows that current flows through this piece of wire. So to begin with, on the left, if you just have that magnet and you have the coil, it's connected to the ammeter. If the magnet's stationary and the coil is stationary, you're not going to have any current, induced current. You're not going to see any movement on that ammeter. However, if I then take my magnet and I bring it closer to the coil, I've changed the magnetic field through that coil by moving it closer, I will then induce a current to flow. It will flow around the loop in a certain direction, and we'll get the ammeter to show the current's flowing in a certain direction. If I then take that bar magnet and pull it away, I've again changed the magnetic field through that loop. I've reduced the amount of magnetic field through that loop. And I will induce a current to flow. It turns out that since I'm reducing the magnetic field instead of increasing the magnetic field through the loop, I'm going to actually induce a current to flow in the opposite direction. So that's why in this picture here, we show the ammeter moving in the opposite direction to the first, as opposed to the first movement there. I think, I'm not even sure how, I pointed out the last one, the faster you move that magnet around, towards and away from that coil, the greater the current you're going to induce. It's a larger voltage you induce, which means you push more current. So here we have essentially the same setup I was just showing you. We have this coil of wire, and each end of that coil is connected to these leads, which are other wire, which are connected to our amp meter. Right? So that little meter is just showing if there's current flowing, if it flows in one direction, or it flows into one of those leads, the amp meter is going to flip in one direction to show there's current flowing in a certain direction. If current flows into the other side, it's going to show the other direction. But either way that it flips is showing that current is flowing in this circuit. Even though besides that magnet, there's no voltage source, there's no battery, there's no power supply, there's no wall outlet. The only thing that's causing current to flow in this circuit is the movement of that bar magnet, and beyond that, the changing magnetic field or the fact that we're changing the magnetic field through the loop by moving that bar magnet. So you pull the magnet out, we saw a little bit of current flow, put the magnet back in, you see some more current flow in the opposite direction, pull it out. So you can see that the direction of the current flow changes based on whether you're putting the magnet in and pulling it out. We're also seeing now here, if you go just very slowly, you move the magnet slowly out, you get a little bit of current flowing, versus if you move the magnet quickly out, then you get a lot of current flowing. Okay, so why is this useful? Well, I've hinted at that, the usefulness of this, when I was saying that without any source of power apparently there, voltage source apparently there, we can cause current to flow. We can induce current to flow. You do that just by changing the magnetic field through this loop, these loops of wire, or any single loop. You can stack a bunch of loops together. So that becomes very useful. If I have a setup, sort of like the one or having a magnet similar to the one in the video earlier, this big C magnet, right? In that picture on the left here, you have this big magnet, right? In the North Pole, you have a North Pole and a South Pole. So there's a magnetic field in between those two ends of that magnet. And given now that there's a magnetic field in that region, if I take this loop of wire and I put it on some kind of axle so it can rotate around, and I crank that wire around, right? I start spinning it. What I'm doing is, well, when that wire is vertical, there's a magnetic field going vertical too. There's no magnetic field through that loop of wire. But as I turn it this way, now there's a whole bunch of magnetic field through that wire. So I've changed the amount of magnetic field through this wire. And again, if you change the magnetic field through that loop of wire, you're going to induce a current to flow. So by just spinning this loop of wire within the magnetic field, I can actually induce a current to flow in that loop. And you keep spinning it, and we're going to keep inducing current to flow. So basically, you give it a magnet and a piece of wire, you spin that loop of wire inside of the magnetic field, so that the magnetic field changes to that loop. We can induce current to flow, which we can then use to, say, light a light bulb. So this idea of electromagnetic induction is the basis of essentially all power generation, all electrical power generation. Here we're showing where we see a hand crank, where it's essentially the same idea. All you have is a crank, but that crank is either rotating loops of wire, or alternatively you could have big loops of wire around a magnet and spin the magnet around. So you're doing something, probably just spinning loops of wire inside a magnetic field, and that generates a current that then lights this light bulb. Bigger picture, if you take something like a flow of water, or places in like a dam where you have a very high pressure, or lots of water up here, another level of water down here, there's a very high pressure where water wants to flow between those spots. So you can use that water to push something to start rotating, a turbine maybe, like in this picture here, a big fan basically, where you rotate around with the water. And all you really then need to do is set it up so that that turbine, that motion of the turbine, will then turn a different element. Here it's called the rotor and the stator, but the rotor is essentially has a bunch of magnets essentially around the outside of it, and the stator has a bunch of loops of wire placed around it as well. So when it rotates, the magnetic field from all those magnets is moving and changing through the loops of wire in the stator, and you can generate electrical current. So just taking the power of water to rotate a turbine, you can generate electrical current. So this idea of electromagnetic induction, like I said, is like the backbone of how we have electrical power at all. And the other ways that we generate power often are through like fossil fuel plants, burning fossil fuels. And all that is doing is creating, you burn something so that you boil water, you create steam, and you use the pressure of that steam in order to turn a turbine. We're back to the same picture. Even nuclear power. Nuclear power, all the nuclear power is doing is the nuclear reactions, the nuclear decays, the energy that's given off by those heats water, that water turns into steam, you use steam to turn a turbine. So it all comes back to this electromagnetic induction. Most of it, I should say not most of it, because like I mentioned a while ago, solar power is a bit different, where you're actually getting electrical current generated just directly from light, from photons. But wind turbines also use the same idea. You know, you're turning a big turbine. The wind's just turning the turbine already. So there you go. You just turn the turbine, you turn some magnets, turn some loops of wire, you can generate electricity. Okay, so just in case you don't believe me, let's see a little demonstration of that. And this is a demonstration with a hand crank electric generator. So in the picture here, there's the crank is on the left side, and the way that the loops of wire are set up is a little bit more complicated than just this very simple picture that we had before. But basically it's a bunch of loops of wire, and those loops of wire, when you crank the wheel there, are going to spin, and those loops of wire, the coils, the loops of wire all together make up this coil, and the coil is then spinning inside of this magnet. So all we're doing is spinning coils of wire inside a magnet, and the ends of the coil are connected to these leads, to this other wire. It goes out and connects to a light bulb. So as you spin that thing, you're going to start to see the light bulb light up. So right now it's pointing out to where the coil of wire is, and it can rotate. The coil of wire is then connected. It's a little bit more complicated than just connecting to the leads, because you have to do this little contacts that can move there a little bit. But the idea is those wires are connected then to this light bulb. You start turning them, you generate current that then heats up the filament in the light bulb, and the light bulb then gives off light. There you go, you just generate electrical power just by turning a crank. So just in case you were thinking that, well, why don't we just turn cranks more and generate more power, or turn them faster and generate more power, induce more current? It turns out there's a counteracting effect where essentially when you induce current to flow, and we'll get into this a little bit more in a couple of slides, you induce a current to flow, well, now you have a current flowing, that current creates its own magnetic field. So you also, not only do you induce a voltage which drives a current, you also induce a new magnetic field, and that magnetic field will oppose the original magnetic field. So essentially the faster and faster you try to spin a coil around, the more that coil is going to become a stronger and stronger magnet that tries, essentially works against you trying to spin it. Right, so that leads us to one of the laws having to do with electromagnetic induction, which is known as Faraday's law. And I've kind of already given or indicated part of it, where Faraday's law essentially tells you how much current is going to flow given the strength of the magnet that you're using and the amount of coils and how fast you're moving that magnet, or amount of loops in the coil. So if you're going to produce voltage, you're going to induce a voltage with a magnet, then right, you got to use a magnet usually and move that magnet through some loops of wire. In this picture here, we just have varying amounts of loops of wire, from 2 loops, 4 loops, 6 loops, right? So more and more going just larger and larger loops. And it turns out that the amount or the size of the induced voltage, which directly leads to the amount of current, the induced current that's going to flow, it depends on how many loops make up this coil, which essentially is just the fact that if you have one loop and you move a magnet through it, you're going to get some current. If you have a second loop and they're connected together in a coil, essentially you're just getting double the effect. Right? You're getting the amount of voltage you're inducing in the one loop, but now you have 2 of them, so you're sort of doubling the effect there. Right? So the amount of voltage that you're going to induced, the amount of current you get to flow, just multiplies by how many loops there are. And as I've indicated before, the movement of the magnet also affects the size of the induced voltage and therefore the amount of current you induce to flow. So you move a magnet faster into a loop of coil, or into a coil, you're going to get a larger current flowing than if you move it slowly into the coil. Again, there's another clip here where essentially it's just showing 3 different coils, small, medium, and large coil connected to a current meter, and just showing that when you move a magnet with about the same speed, so the same rate of motion, rate of changing that magnetic field through those loops, if you move a magnet through those loops, you'll see that the larger coils, ones with more loops, show a larger induced current. Maybe we'll look at that right now. If you want to, go ahead and just hit pause and check on that. Check out that link. Okay, so hopefully a pretty simple question for you then. More voltage is induced when a magnet is thrust into a coil, A more quickly, B more slowly, both A and B, or neither A and B. So take a second and decide which reading it is. Hopefully you said A, because like I just told you, the size of the voltage, the amount of induced voltage you get, is proportional, depends directly on the rate at which the magnetic field changes through that coil. Translates to, well, if you have a magnet, that's the source of the magnetic field, so when you move it, you're changing the magnetic field through the loop. If you move it quicker, you're changing the magnetic field faster. So faster moving magnet, larger induced voltage, which in turn would say there's a larger induced current as well. Okay, so the last 2 topics here. First one is how these things called transformers work. So transformers are another very essential component in our everyday life, modern technology. That is because it turns out that different voltage levels are useful in different situations. So for instance, the batteries, most batteries, AA, AAA, those sorts of batteries, have a voltage difference of 1.5 volts. And that's useful to power a light, so power a flashlight, power all kinds of things, but it's a fairly low voltage. And similarly, when you plug your phone into an outlet, the voltage that is coming out of that phone charger, the voltage that that phone charger is setting itself at, is usually, I think, 5 volts, so a little bit more than that battery, AAA battery, but still not that many volts, or not that high of voltage. But in other cases, like transmitting power, right, all the power lines that you see around, where eventually they start from a power plant somewhere that's generating that power in one of the ways that we talked about just a little bit ago, and that power needs to be transmitted then to your home, to the school, to hospitals, to all the places that use the power. It turns out that when you transmit that power, you're always going to lose some of it. Some of that power dissipates in that transmission. And I think we talked about that in the last lecture in talking about current a little bit. And how you heat up things a little bit and you lose power that way, you lose energy that way. It turns out, though, that when you transmit power at very high voltages, there's overall going to be less power that's lost in transmission. So that's why at least one situation where very high voltage is useful versus very low voltage, like charging your cell phone. So how do we get from a high voltage to a low voltage? We generate power somewhere, it's at a particular voltage level, and we want to transform it from, say, a very high voltage level to a very low voltage level. Right? Maybe from our high voltage power lines, it needs to be transformed down to come into our house, and then from our house it needs to be transformed down again, go to our phones. Well, we can do that using transformers, and transformers work off the property of electromagnetic induction. So down here, let's say we have a picture of a transformer, a very simple diagram of a transformer, and essentially all that makes up a transformer is 2 loops of coil. or loops of wire to make up a coil. So on the left side, say we have this loop of coil, or this loop of wire that's making up this coil, and this is the source of our current. So current's flowing into this coil, and well, since there's current flowing, there's charge moving, it's generating a magnetic field. So you get a magnetic field generated from this first coil, which then part of it goes through the second coil. And the only thing that this core, this square thing, is doing is it's some kind of ferromagnetic material that kind of directs some of the magnetic field from the first coil to the second coil. You don't actually need it for a transformer, it's more for the efficiency of the transformer. And the only thing we need is that first coil, some of its magnetic field that it's creating through that current moving, is then going through that second coil. So if the first coil has AC current flowing through it, meaning current's not flowing the same direction the whole time, if it was flowing the same direction, we'd have a constant magnetic field that's being generated. If instead it's an AC current where current's flowing one direction 1 second and then back the next second, right? So current constantly going in a different direction, meaning the magnetic field that it's generating is constantly changing as well. So when you have an AC current in that first coil, you have a changing magnetic field that's then going to be going through the second coil. And now a changing magnetic field through a coil, we have electromagnetic induction, we're going to produce a current, we're going to induce a current in that second coil. And it's going to be an AC one as well, because the magnetic field is constantly changing direction. So the transformer takes current from one loop, and through this process of electromagnetic induction, through this changing magnetic field being produced by that first loop, going through this second loop, we induce a current in the second loop. Not through any direct movement of current flowing from one to the other, just from electromagnetic induction. And yeah, so that's the basics of a transformer. Essentially there's two forms of transformers, a step up and a step down transformer. So they're just like they would sound, right? All they're doing is changing voltage. They can change voltage levels. So in a step up transformer, you're going from a low voltage to a higher voltage. So maybe you have an AC current coming in at a voltage of 5 volts. You can step it up to 100 volts. The thing is, you're going to get less current coming out because overall the power will be the same. But don't worry about that too much. So in a step up transformer, all you really need to do is have more coils in the second loop, and they're in that, or more loops, in the second coil, the secondary coil, than you did in the first one. And we don't need to go into the details, but the result of that is that the voltage you get out of the second coil, the secondary one, will be higher than the voltage in the first one. And it's actually, the ratio of the number of loops will say how much you step up that voltage. So similarly, or I guess contrarily, the step-down transformer is one where the loops in the primary coil, the first coil, are more than the loops in the secondary coil. So if you have more loops in the first coil, where the current actually is flowing in, then you'll get a lower voltage on the secondary coil, where you're inducing that current. And at the bottom here, we just have a nice little picture of all these different places where transformers are used. So the power plant generates power at a certain voltage, say 12,000 volts. You have step-up transformers that then push that voltage up, right? So step-up transformers means there's a primary coil where that current flows in from the power plant. The secondary coil has more loops in it than the primary one, and we end up stepping the voltage up to, in this case it looks like 240,000 volts. And that's that very high voltage that we can transmit our power and not lose very much of that power. But then eventually you get towards where the homes are that want to use that. That high voltage could be dangerous inside of, in a very close setting where there's a lot of things that will conduct electricity. So you need to step that voltage down. So you have a step-down transformer, which steps the voltage down to, say, 7,200 volts. And then you have another step-down transformer, which is the ones that you actually usually see on power lines and power poles, kind of cylinder-looking things. And they'll step the voltage down to 240 volts. And then finally within your home, you plug into a wall outlet, and that part of what that little box is doing when you plug it into before you plug in your phone is it's transforming the voltage from an outlet all the way down to like a 5 volts, which your phone can then use. It also does something else because your phone needs a DC current, a direct current to flow in order to charge it. What comes out of the wall is AC, so also what it's doing is converting an AC current to a DC current. You don't need to worry about that too much. So again, just to reiterate that a DC current will never work, or a transformer will never be able to transform a DC current. The reason being that you need an AC current on the primary coil because that AC current will produce a magnetic field that's constantly changing, it's constantly flipping back and forth as the current flows one way then the other. So that changing magnetic field through the second coil is actually then what will induce that voltage, which will induce the current to flow. Okay, so the final topic here is what's known as Lenz's law. So this is another law that has to do with electromagnetic induction. And I put here as Lenz's law is basically about induced magnetic fields. So I hinted at that earlier, where we're talking about this no free lunch thing, where if you induce current to flow, then you're also inducing a new magnetic field that arises from that current. Yeah, so let's go back to a picture then from earlier where you had a coil, and that coil is connected to a meter so we can see if current flows in that coil. And if you take our bar magnet, right, you take the bar magnet and you push it towards that coil. I told you, and then we saw in a demonstration, that you're going to induce a current to flow in that coil, and you'll see the ammeter will show that by deflecting one way or another. Okay, cool. We can induce a current to flow. So simplify that picture a little bit, where instead of the whole coil, just imagine one loop of that coil. Let's think about one loop, right? And then we have this picture here on the right. So you have one loop of coil, or one loop of wire, and when you move a bar magnet into it, you're going to induce a current to flow in that loop. So now, go to this picture, the final picture on the right here, where now we have current flowing in this loop, the induced current that we've caused to flow because of this external magnet moving in and out. We have current flowing in this loop, but again, it's kind of a cycle where now we've induced a current to flow. That current itself is going to generate a magnetic field. And as it turns out, and shown in this picture, when you push that magnet in, you're going to induce a current to flow in a certain direction such that it makes a magnetic field that will repel the magnet, or will oppose whatever change that magnet is doing. So when you're pushing a north end in, the current that you induce is going to induce a magnetic field from that induced current with the north pole pointing towards that north. It turns out then if you pull the magnet out, you're going to induce current to flow in the opposite direction, which will then have an induced magnetic field with a south pole on that side, which tries to pull the magnet in. So you try to push a magnet in, you induce a magnetic field that tries to push it out. You try to pull a magnet out, you induce a magnetic field that tries to pull the magnet back in. So Lenz's law is essentially telling you that nature and particular magnetic fields and induced currents, they don't really want things to change. So to begin with, if you have just a loop of wire, there's no current flowing in it, and you take a magnet, you try to push it in, you're trying to make some change happen. The overall picture is the loop tries to make it so that doesn't happen. So the end result is that the loop creates a magnetic field so that it wants to push against that magnet coming in. And then again, if you try to pull that magnet out, the loop doesn't want that to change either. It already has a magnetic field in it, doesn't want to remove it now. It's going to produce a magnetic field to try to keep that magnet in. So this is partly why you say that you can't have a free lunch by just moving a magnet in a coil or moving a coil within a magnetic field in order to produce more and more current. It's because the faster you move that magnet, the more current you're going to induce, the stronger magnetic field you're going to induce, and the harder it's going to be to move that magnet. Right? Because any way you move that external magnet, the coil is going to do something to oppose that. Alright, so finally, what we just saw is that if I try to move a magnet through that loop, the loop is going to create a magnetic field that's going to stop me. And if I try to pull that magnet out, the loop's going to create a magnetic field in the opposite direction that tries to stop that as well. So you try to push a magnet in, the loop tries to push it out. You try to pull the magnet out, the loop tries to pull it in. A nice little demonstration of Lenz's law. Yeah, right, so you take the loop idea, that loop, and just elongate that loop. Imagine stretching that loop out, we get the cylinder. The cylinder is essentially just an elongated loop. So the same effect's going to happen. If I try to push a magnet into that cylinder, the cylinder is going to get that changing magnetic field through the cylinder. It's going to induce a current to flow. That current's going to create its own magnetic field that's going to oppose the movement of that magnet. So you try to push a magnet in, the cylinder is going to try to stop it from moving in, or stop it from moving more in. Or you try to pull a magnet out, that cylinder is going to induce a current in the opposite direction. It's going to induce a magnetic field in the opposite direction then to try to keep that magnet in. Think about what that means. That is essentially that if I try to drop a magnet through this cylinder, what's going to happen is that magnet is going to constantly have an opposing magnetic force that's going to push against its weight. So if I just drop the magnet, try to drop it straight down through the cylinder, there's going to be a constant magnetic force that's opposing that gravitational force that's pulling it down. So instead of just dropping down like it normally would, it's going to drop down pretty slowly. It's a very odd thing. So this guy, first, he has a piece of metal and this metal cylinder. He drops it down, just falls straight down. So he switches out that piece of metal for one that's actually magnetized. And a very strange thing happens. That magnet doesn't just drop straight through, right? It's creating by its movement through that cylinder, it's creating a magnetic field, or it's inducing a current to move around that cylinder, and that current is creating its own magnetic field that opposes the motion of that magnet. So somewhat of a sort of neat trick that is a consequence of Lenz's law, and a good demonstration of it anyway. I think that last demonstration was technically like a magic trick, but as you might know, or as the saying goes, any sufficiently advanced science or technology seems like magic. Cool, so that's it for electromagnetic induction and magnetism. Hopefully it's not too long and you get through it all and you're ready for the next exam. So this is the last lecture before our third exam, and that exam is going to cover all the stuff that we did since the previous exam. So all the stuff on waves, vibrations, sound, and then now into electricity, current, magnetism, and electromagnetic induction. And okay, that's it. So have a good night, or day, or morning, or afternoon, whatever it might be. And I wish you well. Adios.